Okay, I think we've reached the hour, and the number of participants appears to be leveling off. So we'll begin. Good afternoon, and thank you very much for joining the latest webinar in a series of webinars, which are collaborations between the school program at ARM and CBSE. So this one is called Contexts Are Key. And contexts, as you will explore in the training session, are really at the core of successful PBL projects. So this will really help you, for no matter which subject discipline you teach, to contextualize your projects within the classroom. Just a couple of housekeeping points before we get started. Because of the number of participants, we'd ask that you use the Q&A box for any questions that you have. My colleague Rob and Surya will be answering them as we go along. And we'll also pick out questions that are asked to address within the Q&A at the end of the session. Another point is that certificates will be emailed out to you after the event. So we often get questions about how to access certificates, and that's the answer there. It will come to you with a link to the recording of the event post-event. And just a final point, which is that if you are experiencing any sound issues throughout the presentation, we just ask you to check your connectivity at your side. It's often this is the cause of any of disruption to sound quality. Okay, so moving on, this is our agenda for today. So my name's Nick Sample. I work within the school program with my colleague Rob Lehman. I will start by just introducing a program, the program that we work on, and how that can support you as teachers. Show you where you can find more information about what we do. We'll cover that as quickly as we can before we get into the main professional development session. Before we do move on to talk about the school program, I'd just like to thank again CBSE and Dr. Singh and Mr. RP Singh for supporting us in creating this series of webinars. Okay, so I've got a comment there about the voice not coming through. I think that's likely to be a local issue. So just ask you to check your your audio settings. Okay, let's move on to the first part of it. So just a brief introduction to your speakers. So both Rob and I, we come from an education background and started on the school program here at ARM about 3 to 4 years ago. Rob, would you like to say a few words about your background in the context of the main training session that you'll be running shortly?
Sure thing. So I started life as a network engineer, and then started teaching computer science and IT in schools many years ago. Then started working at an exam board called OCR, which is part of Cambridge Assessment. You may be familiar with Cambridge International. They worked there reforming IT and computer science qualifications in the UK and internationally. Worked around assessment products and support to teachers, and then moved across to working at ARM on the school program.
Fantastic. And Cambridge Assessment is something that we both have in common. Most of my career I've spent with Pearson, working across schools and higher education before joining ARM in 2018, when we set up the school program. So the school program, this is our vision: to empower all learners with the opportunity to develop the interest, knowledge, and skills that enable a lifetime of engagement in STEAM. And this is really something that we strive towards in the work that we do with schools and organizations internationally. Our program is really comprised of two elements. One piece, and they're very much linked together. One is community and research. So we do a lot of work with organizations that within them house communities of practice of teachers. So this would be in the UK, in the US, and also with CBSE, of course, in India too. So this is about enabling groups of teachers in best practice with connection to computing, computer science, and other STEM subjects in the classroom. To support this, we have a range of content and training available. Webinars such as this one, so live events, but also, and we will talk about this in a few points, free to access professional development on the platform edX.org. To complement this, we have a range of free to access lesson plans, project books, presentational materials that you can access from free of charge, again, from our website, school.arm.com. Let's just quickly take a look at that. So if you go to that website, you will find, this is what you'll see at the top of the page, a range of different resources linked to. And right there at the top, you'll find a link to a brochure that we uploaded there very recently. And that brochure is designed to answer the question, how does the ARM School program help teachers and learners? So we'd really recommend going to our website, clicking on that link there, where the yellow arrow is pointed towards, and take a look at our brochure for a full explanation of the range of support we offer. On the website as well, you can also go to the bottom and very, very quickly sign up to our newsletter, where you get regular updates on new content and training opportunities provided by our program. So a couple of slides ago, I talked about the professional development that we offer on edX.org. Now you can find that if you search for project-based learning on edX, as you can see in that text box. And there are 4 courses there that really cover a range, really end-to-end, the full range of everything that you might want to know about in connection to the application of project-based learning with physical computing devices such as microbit, Raspberry Pi, and Arduino. So how to use those effectively within the classroom. Now we advocate for PBL as a effective pedagogy, but this isn't intended to replace your everyday practice, rather to supplement it. So it's an extra string to your bow as teachers. It might be that you decide to do a PBL class once a semester, once a term, a couple of times a term. That's really down to you as teachers, but we do, based on the evidence, we really do recommend trying to integrate this into your STEM and computing lessons as far as you're able to. So the kind of themes that we're covering within the webinar series with CBSE really link to the courses here. If you feel inspired by one of the sessions, we'd certainly recommend that you enroll on the courses, which is free to do, and explore them in more detail at your in your own time, at your leisure. Okay, and on the training schedule, this is the full range. You can find recordings for the first 2 sessions. We're now in session 3, contexts are key. You can find recordings for the first 2 sessions in the link that was sent out to you to enroll for this one. So on that page on arm.community, you will find recordings of the sessions that we've done so far. This one will also go up there, and we'll be adding to them as we run through future sessions all the way from here to April of next year. Okay, so that's a whistle-stop tour of our program. I think we'll now start the main training session. Again, if you could please put any questions that you have within the Q&A box. And just a reminder that certificates will be emailed out to you after the event. We will address any questions in a Q&A session after feedback. My colleague Surya will say a few words about feeding back on the session. We'll go into Q&A and we'll do some live discussion with Rob about some of the questions that come up in the main session. Okay, thank you very much. Let's get started. Over to you, Rob.
Thank you for joining us for this session all about contextualization and how contexts are key in project-based learning. So these are the learning outcomes for today's session. We're going to start by looking at the ASP schema and looking at how we can use this as a template to navigate and design and develop project-based learning experiences for our learners. We're going to look at how to use a given context or a set of given contexts to the ASP schema and how to develop engaging and effective problem sets for our learners to engage with on these projects. We're also going to look at how to create differentiated or scaffolded resources and how these can help deliver these projects effectively in the classroom. We're going to look at the hardware considerations and other considerations when we're developing these projects. And then we're also going to look at how to create novel and new projects depending on which subject or topic you want to cover in your subject, and then how to develop and iterate on those projects. So that's what we're going to be covering today. So as a reminder, here is the big picture of project-based learning and practical computing as laid out in the ASP approach. And we've covered in previous sessions, and also we will cover in future sessions, all of these different elements. But the bits we're going to focus on today are the green sections here. So we're going to be looking in specifically what project-based learning is all about, which encompasses all of the ARM School program schema. We're going to be looking at how we can cover different types of curriculum and how we can engage those learners using various different contexts, and looking at how we can solve real engaging problems. And all of this comes together. There's quite a lot of moving parts when pulling all these elements together, and it's we're going to go through step by step what we need to consider when designing and developing these contexts and problem sets and projects, and look at all the things we need to think about to design something which is really effective. So what is the ASP schema? This is something you may have come across in some of our previous sessions, but we're just going to go a little bit more of a deeper dive into what they all mean. So the schema itself is those 5 categories you can see on the left hand side. So getting started is how we introduce the context or the concept or the subject area for our project to our learners, and it's where we lay out this scenario. Now this has to be something that the students are going to be familiar with, something that they can find relatable, or at least it's better if it is something that they're familiar with, because it lowers the the confusion around the project. And if it's something which is they're already engaged with, or something that they're already familiar with, be it a subject or a local context, perhaps it's a cultural theme or a cultural trope, and this will make the accessibility of the project much more effective. This also allows us to develop a human narrative around this. We find that something which disengages learners is when they can't relate to the problem or the project, and it just seems like you are doing the project for the sake of the project rather than trying to solve a real problem. So it's a really good opportunity to weave in a sort of a human-centric narrative around why are we doing what we're doing, what problem are we really solving, who is this really helping, what are we improving in the world to make it a better place for everybody. So it's a really important piece to get right about why are we doing what we're doing. And this has to be carefully crafted alongside the success criteria, which is arguably the most important piece of this schema. So the success criteria can be thought about as learning outcomes or simply as objectives, and these are laid out in order of complexity, and they tend to start as quite constrained and then move on to be more open-ended. They should start with being something simple yet achievable, so which allows all learners to get started with a project and do something relatively easy. And then it needs to open up as it works its way through. And for younger learners, this might just be 3 or 4 success criteria, but older learners, you'd expect to be able to do a little bit more, but this is a key part to get right, because the success criteria is the objectives which everybody is working towards, and they have to be achievable, they have to be related to the context which we're building for, they have to be able to work with the hardware that you're working with and with all of the constraints, which we will come to a little bit later on. But just bear that in mind, that the success criteria is the bit which is you'll spend the most time crafting, and you'll find that when you start to write a context and then some related getting started material or success criteria, that these things have to kind of bookend each other really effectively in order to be successful. And so yes, these are really important. The pro tips is the next important bit of this. Now this is effectively the scaffolded support, so this is how you can differentiate or support learners in what they're doing. This might just be a single line. You'll see this in the ARM School program resources, where we have box outs for a tip, and it might be a link to a website where there are some additional resources. It could be like, watch out for this particular physical feature or thing that you might trip up on when doing these projects, or it could be something slightly more resource centric. So it could be a cheat sheet. Now this is something which will have like code references if you're doing computer science, or it maybe have some formulas on there if you're doing maths or physics or something similar, or it may just be a resource which adds a little bit more richness, a bit more detail to the project that they're doing. And it could even be as far as partial solutions. So this may be useful if you've got mixed ability groups, or if you think that there's a risk that students are going to disengage at some point if they get stuck, and if you don't have time to intervene with all of these groups. Let's say, for example, you're teaching a large low ability group, then having some snippets of solutions may be useful in that context, because it will just get them started without necessarily giving away the entire solution. So it's worth having these at hand to help them. So a pro tip is effectively the scaffolding, but also it's an accessibility tool to help learners get moving, but without giving the game away. The next one is stretch tasks. Now these can be used in different quantities, and they're effectively additional success criteria, but they're crafted in a slightly different way, in that they add complexity to the project. So this allows you to upwardly differentiate. So they may build on the learning that you want the students to achieve. It may add in additional complexity in terms of the project. It could be a physical attribute which is made more complex. It could be a programmatic element which is made more complex. It could be additional features. So for example, a programming project may have it needs to have 3 interactions or 3 features, and the stretch task will be make 5, but it has to have these additional features or cater to this particular audience or user or something like that. So it's a way of building an additional challenge which doesn't take them off piste in terms of take them in almost into a separate lesson. It should be related to the original success criteria, but just going into more depth and going a little bit further and adding in a bit more complexity. And it's a way of keeping the more advanced learners or the fast learners on track, and just giving them a deeper understanding about what they're doing, and making a more sophisticated end product, but still on the same sort of on the same project as everybody else. And then finally is the final thoughts, and this is a really nice way of tying up a project. It's getting them to reflect on what they've done and why they've done it. It's a case of, have they met all of the success criteria? Have they met all of the stretch tasks? And how is what they have done related to the context which was set out initially? Have they met all of the objectives? Have they done it effectively? What would they do better next time? If they had access to more resources, what would they improve? So this is a really good way to, once they've seen the sort of the initial concrete real life example that they're going to be working on and they're getting started, then we've unpacked that and explored it through the success criteria and support material. It's then a way of repackaging all of this content and making it concrete again. So this is that sort of semantic wave approach, and it's a nice way to build in other things as well about how this project relates to the wider world, the bigger picture. How are they improving the world based upon what they've done for their project. So it's really important to have a firm grasp about what these different elements of the schema do and how they work together. And these are effectively going to be used when creating project-based learning projects as the headings in the document. So it's effectively think of it as like a lesson plan or an activity sheet, and you'll have those 5 headings, and you may have multiples of the pro tips, for example. You'll generally just have one getting started. You'll have one area for the success criteria, but you'll have several success criteria. You may have multiple pro tips. You may even have whole exercises in the pro tips as a starter exercise for the project, and then you'll have additional stretch tasks towards the end, and then so there could be multiple stretch tasks and pro tips depending on how you structure the project, and also depending on the age and ability of the learners that you're working with. And then obviously the final thoughts always comes at the end, but that's a sort of a loose structure of the ASP schema and how it all fits together and what it means. So this is quite a useful framework to create these projects in, and it just makes it consistent. So that's the schema. These are the other core elements of the approach. Now these are sort of specific tools that we look at when creating physical computing projects. So there's input, process, output, which I've talked about in previous sessions. There are the soft skills, or full on 6 C's. So this is all about collaboration, communication, and the others as well. And so an iterative development cycle. Now this is something which is often seen in design and technology circles as well as computer science, and it's this concept of iterating through a problem multiple times and developing it and improving it as you go through. And it's important to bear that element in mind, because you'll see that when you're crafting success criteria, it's worth thinking about how they will relate to each other in terms of how many times a student will need to iterate through a problem. And also this element of design first, so actually getting students to think about the problem that they're attacking and designing a solution to it before they get off. So we'll explore all of these in turn. So this is the IPO model, or the input process output model, and it's worth spending a bit of time going over this again. I've touched on this in previous training sessions, but it's really important to teach your students to be able to analyze project-based learning problems and contexts using this model, and it helps with almost everything in IT, computing and engineering. So thinking about what are the inputs into this problem, how do we process those inputs, and what is the output that we want to see from this. So it's really, really useful, and it's particularly when you're talking about physical computing, because there's always going to be some sort of input. It could be something as trivial as a button press, or it could be a temperature sensor, for example. Something is going to be done with that process. For example, the button may trigger an algorithm, or just a simple output, such as making a light come on. Or if it's something like a temperature sensor, there could be some slightly more complex processing, such as whether the temperature goes above a certain threshold, which then may trigger the output of a fan or something like that. So it's a really, really useful way to train students to think about what are the digital and analog inputs, how those inputs are then processed, what logic is applied to those to that data, and what we can meaningfully output to solve the problem that we're trying to achieve. And it's really, really useful to train students to use this as part of the design process. And you can do that quite simply by giving them a table. So here's a good example of an IPO table, and as part of the scaffolding for the learners, you might want to give them a clue. So this might be a sort of hint towards the first success criteria, for example. And this is obviously quite a generic one, but the input would be a button press. The process will be that it records some data through one of the other inputs, and the output might be a graph on the LED screens, like a bar chart or something like that. So you can have this, get students to do this on whiteboards or do it on paper. There's a multitude of different ways to get them to think about it, but getting them to think about it is really important. Students will struggle with this initially, and it's important to get them to think about all of the different types of input that they're going to have as part of this, and we're going to look at lots of examples of this later on. And just working out what inputs there are is the first step. It's then working out what type of data does that produce on the board, and then how can you then process that? What logic can you apply to it? Is the data stored? Is it transmitted? That's all part of the process and the output, really. What sort of things do we want triggering as an event based upon how that data is processed? So there's lots of things to think about there, and that's where you build in all of the sort of computational complexity in terms of the algorithms that they're going to be writing for this, and they need to design those at least briefly before they sort of jump in and start doing it. And this is a bit that students don't necessarily always enjoy, but it's certainly worth spending the time getting them to write out IPOs, for especially when you get more complicated projects. Another element of the design thinking is something that we have templates for, but it's getting them to think about the bigger picture. So let's say you give them a concept or a problem or a product, and it's worth thinking about this in terms of a product, because it's almost this productization of a problem. And the MicroPet project that we've looked at previously in other sessions is a good example of this, where you would get them to think about who the users are of this particular problem and think about what would their needs be. You know, what do they want to see? With the MicroPed, it's all about interaction. So you'd have to get them to think about what types of interactions would this user use. You know, what are the success criteria, and how do you meet them? It's also worth thinking about what materials they've got. So it brings in this kind of engineering mindset, this physicality all around physical computing, and what limitations does the materials that they have available put onto the project. You know, can they design a solution to this using the material that they have? It's worth getting them to sketch and visualize what their product will look like before they do it, and also getting them to think about the branding. So it's always worth sort of adding an element of rapid prototyping, maybe a bit of business studies into this. So thinking about what would their sort of team logo or product logo be, and that also allows you to add in some additional challenges, such as getting them to present their ideas as a group, which helps build group cohesion, and it helps with those full and 6 C's. It's also getting them to think about what features do they want to design into this, and this will link to the IPO table that we've just looked at, and analysing what those features are, what they need to happen, what inputs they require, what logic needs to occur, and also what's the prioritization of all of these features, and that you should draw their attention to the success criteria to make sure that they're doing it in the right order, because as they add some features in, it may change others. So it's worth thinking about that as well. And then this also can act as a sort of an area where they can do the reflective exercise and a way to capture that. So when they get to their final thoughts, they can think about what could be improved in their project, and it may be something, depending on how you want to focus the lesson or the project, but it may be about thinking about what additional materials they might have. Maybe they'd want to spend more time thinking about the algorithms or the branding. You know, it really depends on what the context is and what area of the curriculum or whatever topic within your subject you want to draw the learner's attention to. So it's a really good idea to have something like this. And again, you can get templates for these on the Arm School program website and use these, or you can create your own, because it is just essentially some boxes that they fill in to get them into think and design other elements outside of the sort of the core functionality of it. But we really encourage you to get them to design stuff before they make it. So this is the iterative development cycle, which I touched upon previously, and it's a really good idea to explain to students what this is, because one area where students can often disengage is where they see the success criteria, they try to achieve it, they don't plan it, they just go straight into development, it doesn't work, and then they disengage. And so you have to drill into them this idea of fail early and fail often, that they are not going to have a perfect product first time round. They have to look at the success criteria, they have to plan and design what they're going to do, and then they have to develop it. And there may be a mini cycle in there where their development may mean that they can't carry out their design, and so they have to go and rejig their design. And that's absolutely fine. That's all part of the process. And when they are developing it, they have to test it. Now, it could be formal testing. This depends on the age range that you're working with. So it could be like, you know, black box testing, should you wish to, or it could just be checking that the desired outcome from the project is what they were anticipating. And students often forget when they're coding to like flash the boards and, you know, update the code on the boards once they've written the algorithm. So it's getting them to think about this, is that once they've changed something, testing that specific function works, and that specific function hasn't caused other problems in other areas of the program. So it's worth getting them to think about that, and then evaluating, does it meet the success criteria? So has the feature that they've tried to implement actually meet the needs of the success criteria? Because as I'm sure we've all seen, students often will, when they get overexcited about a project, go off and add additional features which are exciting and engaging, but don't necessarily meet the initial success criteria which they are being judged upon. So it's worth, this kind of keeps them in check of or constantly referring back to the success criteria, thinking about how they've designed it, how they've implemented it, testing whether it does what it needs to do, and then evaluating it again, and going through that circle
multiple times during the project. And this is how, well, at first this can be a little bit tricky for students because they kind of want to rush ahead and do stuff, but the more time they spend doing it this way, the more thorough and accurate their projects are. And whilst for sort of smaller projects for younger students, this isn't, they don't necessarily need to be using this constantly. More complex projects, they really do, especially when you've got lots of success criteria which added lots of complexity to a project. So it's worth training students to think about this and at least referring back to the success criteria constantly as a way to assess their own progression. So the other key area then is the soft skills. And again, I've spoken about this in previous sessions, but it's really important to for students to express what they're doing in terms of teamwork and collaboration, and come up with creative ideas. And this all feeds into what the context is. If the context that you're coming up with for your projects is exciting and it's something that they're familiar with, the students will be able to communicate about it and collaborate in a way that they can come up with something creative and innovative much more easily. And so it just sort of smooths out that learning curve if they are already, all of the group are already familiar with a particular problem set. And it allows them to apply these computational thinking elements and plan and iterate through a problem set much more easily. And so coming up with a good, solid context and a concept is just helps them express these 6 C's much more effectively. So it's worth planning these sorts of things into the group and reminding students when they're delivering this that they should be talking to each other and communicating effectively. So let's just take a step back a little bit. So we've looked at the sort of the ASP schema and sort of some of the core teaching or pedagogical constructs that sit underneath it. So here's sort of a big picture view about the different things we need to keep in the back of our minds when we are thinking about designing and developing new project-based learning contexts. So there is a physicality around all of this, which is the physical computing bit of it. So there's going to be a making element. There's going to be some sort of device that they're going to be programming. You have to think about the pedagogical elements that we've just covered. Yeah, you have to think about the subject as well. Now that subject could be any subject. Now we tend to talk about physical computing in terms of the computer science world, but this can be applied equally to any other subject, and we'll look at examples of this shortly. But you have to consider what those subject areas are when you're designing these problems, and you have to think about how can we make these problems physical? How can we create an artifact which ekes out the subject topic that we want to explore, and how can we also design these contexts and these problems so that students are demonstrating their knowledge of the subject and also demonstrating their skills in problem solving towards that subject goal. And they do that through this pedagogical approach of creating these project-based learning. And it's really is those 4 things in sort of equal measure is how you do effective context and effective project-based learning experiences. And it's that sort of, again, this melding of sort of theory and practice together. And it's difficult to get right. The first time you write one of these, it can be a little bit bewildering because there's an awful lot of different things to think about and you're not quite sure where to start. But once you've done it a few times, it becomes really easy, and you can knock these out really quickly once you become used to it. But this is sort of the top level approach of all the different things we need to think about. And next we're going to look at what contexts are and how we can use this model to write effective contexts. So why do contexts matter? This is one of the, again, core elements of project-based learning, is about why do we need to have something as a sort of a story to tell the students as to why they're doing it. Can't we just get them to just do it for the sake of it? And this really is part of why we get them to do it. Is all about engagement. And a problem should be engaging. You want your students to be excited to learn. You want them to not just understand what they're trying to do, but also want to do it. And it's the sort of classical sort of constructivist approach is that we want them to learn by doing, but we want them to want to learn by doing as well. And that's how you can make this work in a normal classroom and not expect learners just to sort of learn through osmosis. It's about crafting a context which students are going to not just understand, but they can relate to, they'll be familiar with, and it's something that's real to them. And that, I think that's really, really important. If students understand why a context or a problem is a problem in the first place, they're going to be much more motivated to want to engage with it and then apply technology meaningfully to solve it. It also gives them a sense of ownership over their solution. You know, they can see that what they're learning almost by accident is how they can apply it to solve a real problem, and that gives them you know, a real sense of success and achievement, is that they can see that what they're doing is changing the world, or potentially could go and change the world. Even if it's just a model of a more complex solution, it makes them understand that this is valuable to understand, and valuable to be able to do as a set of skills and practices to solve problems. You know, technology can change everything, but it's often difficult to motivate students to want to learn how it works, because it can be seen as dry and a bit dull. But it's linking that sort of real world, accessible, engaging problem, and then how do we solve that problem using technology, and then applying computational thinking skills and other subject domain skills. That's the sort of the sweet spot. It's that confluence of the why as well as the how, and also the what. Also, the context gives us some levers as well. It gives us an opportunity to add in and define constraints around the project. So it allows us to sort of tell a story and set some limitations on what they can and can't do, because it's important to have some constraints on our project so students don't just go completely wild with their solution or what they're trying to design. And so that's a really effective thing to be able to do as part of the context. And these don't have to be complicated contexts. And as you'll see in the examples following, they can be quite simple, but it just grounds the learning with something that the students will be familiar with. And ultimately, it's this it's the why. You know, why are students doing what they're doing? And if they can answer that, then they can see why it's important to do so. And as I mentioned previously, it's this it allows you to add a narrative construct around this. It allows you to tell a story about why they're doing what they're doing, which is really, really important. And I think that helps, certainly in my experience, it helps disengaged learners become more engaged with what they're trying to do if you can explain to them why. So what do we mean by context? I think the first bullet sums it up perfectly. It's the context is the circumstances that form the setting for the learning in terms of which it can be fully understood. And that might seem like a bit of a mouthful, but effectively it's the theme, it's the context, it's the ideas or narrative of the problem around which students can engage with it and understand the challenges that they can relate to in their real world setting. So this all might seem a little bit abstract, but we'll come to some concrete examples of this as we go through. But the context can mean almost anything. And I really mean that. It can be absolutely anything, as long as it's something which has been designed to be relevant to your learner and recognizable, and it also helps if it's thematically linked to their real world setting or your subject or the school or something cultural, something that the students are going to be able to instantly recognize and have some understanding of. And that's really, really important to get the balance right. It makes engaging and accessing these projects much more simpler if the students understand a little bit, almost of prior learning around the context of which the problem is set in. Again, I can't say this enough, is the context can be almost anything, and it's your job as the teacher. You know your students the best, you know what context all of these learners live in, so you should be able to craft a context which is relevant and engaging to them within your subject domain. And again, that can be almost anything. So a good example of a rich source of contexts are the global goals. Now, we use these in the Arm School Programs material, and so do other organizations such as Microbit. And these are a set of problems laid out by governments and organizations all over the world to try and make the world a better place. So it's a really good rich seam of different areas which students will see every day in their lives and understand that these are problems and things that we can design problems and projects to engage with. And you can see really good examples of these, particularly around life below water and life on land in the Arm School program micro course book. which have got really good examples of those, but you can design your own using any of these themes, and each of these themes has sub themes. They've all got sort of usually 5 to 10 sub themes underneath them, and you can pick one of those and develop your own projects around that, depending on what's most relevant to your situation. And the beauty of this is that whilst it gives you a problem set to start off with, you can seek to solve that problem set using any subject. For example, like the Zero Hunger, for example, you could have a project which explores it in English or geography, physics, computer science, food technology. There's lots and lots of different ways to, or different lenses that you can look at these problems and create projects and project-based learning activities on. So if you're stuck for ideas, this is a really, really good source to go to try and think about projects in contexts. But ideally, you want to think of something yourself, and I think the first time you come to this to create your very first project is to think of something off the top of your head which you know your students will engage with. So let's get into some of the nitty-gritty around designing your first project-based learning project. So it's useful to think about project constraints. Now this is looking at it from sort of a teacher perspective, and there's two types of constraints. There's the project constraints, which you need to think about, and then there's constraints that we can set on the learners, which hems them in a little bit in terms of what they're doing. But one thing you need to consider for your project is, first of all, time. How long do you want to commit to working on this project? Is it going to be a single hour? Is it going to be several hours? Is it going to be over a course of a week? It really does depend. How much time you've got will directly dictate how much you can get done. And whilst an hour is enough time to do a small project, the speed of progression to these projects tends to ramp up as they go through them. So sort of doubling that time to 2 hours, you get a lot more done in that time. And if they're spending multiple lessons on these projects, they will get lots and lots and lots done. You can make these projects relatively complex just by giving them more time on a single problem set. So that's the time element. Another one is the hardware. What if you're doing a sort of physical computing projects, what hardware have you got available to you? This might be the type of board that you've got, the type of sensors, the wires, the electronic side of things, batteries, all of that sort of stuff, and also access to IT suites, so PCs, tablets, laptops, that sort of stuff. These all dictate what the constraints of which you need to make sure are sorted, so that you know what you can and can't do with your projects. There's also the making side of things as well. It's a good idea for, and we advocate for, that students have to physically make an artifact, and that's so it might be like with the micropet, a body that they have to make out of cardboard or paper. They have to decorate it and put the device inside the pet so that we can see it working and it's programmable. But you may be limited on what making resources you have available. And there's obviously a budgetary element to that as well. And also, as part of that, is space. Do you have enough room, for example, in a computer lab to be able to be cutting and sticking and gluing and colouring in and all these sorts of things alongside the programming of the elements? So you have to think about your learning space and what you can realistically achieve in that given space. Also tools, when you're working even with simple paper, you need to consider the use of glue, scissors, tape, that sort of stuff, colouring in the paper, just basic stuff like that you need to think about. And you have to be able to store these things securely, and also be able to store the project between lessons should this go across several lessons. So think carefully about all of these different things, and it's often useful to just do a single lesson project to start off with, because that way you don't need to worry about a lot of these things. But then once you get more confident with designing projects, then you can do something over several lessons or several days. And again, this is where these other constraints become more important. And then there's also the flip side of that, is introducing constraints to the learners. So this is something, and again, one of these levers that I mentioned earlier, in terms of how can you add in additional challenge to this. And this might be something you can focus on, like the engineering mindset, so you can give them a very limited supply of making materials. If they're making like the body of a robot, let's say, you could give them just bits of wood or tape or straws or paper or whatever. And so by limiting the access to the resource and the tools that you give them, it adds in additional challenge. But it's worth linking the use of these restrictions or these constraints to the context. Like, why is it limited? Why is it restrained? It might be a cost thing. It might be a sustainability angle. We want to use as little resource as possible to make it as efficient as possible, or it might be something to do with weight or cost or anything. There's lots of different ways that you can add in constraints, which makes the students think about things in a slightly different way. It also might be something limited in terms of the boards that you're using. The different boards can only do certain things. So like a Raspberry Pi Pico is very different to a microbit, or some of the more advanced Arduinos can do a lot more than other devices. So it's worth thinking about what the functionality of the electronics that you're using is as well, and how that is linked to the success criteria, because not all boards do the same stuff, and they all do it in slightly different ways with different levels of complexity. So it's worth thinking about those things as you're building them in. Another constraint is they have to use a specific set of hardware. So it might be a particular board with a particular set of wires or peripherals, or it might just be the board itself if you're doing something like using the microbit. It's also worth thinking about limiting time. Whenever I deliver these projects, it's typically in a 1 or 2 hour session, and you have to constantly remind students that you have to work fast with this, and the pace at which they engage with these projects and start to work on them will ramp up swiftly as time runs out. So just keep them under pressure to be working quickly throughout, because and giving them less time than what they would comfortably like to work with can be a valuable tool in making sure that they're progressing quickly and keeping them in that zone of proximal development. And you can specify these things in the success criteria, and that's absolutely fine to do. And it may even form part of the narrative or part of the story that we tell as part of the getting started. So getting on to the idea of project ideation, there are lots of different ways to slice this. There are lots of different ways to think about what should this problem set be, what problem do we want to try and solve, what element of the curriculum do we want to cover. There's all of these different bits. So whilst we're sort of getting together all the different options and we're starting to think about these sorts of things, just think about what does engage your learners. What area of the curriculum do you want to cover? What subject are we trying to do? Do we want to use some sort of current affairs topic or something in the local news? Do we want to link it to one of the global goals, or do we want to link it to something which is happening in your school? For example, if you're doing a recycling week or something like that at the school, you may want to do a project linking it to sustainability or something similar. What sort of stuff do we want to get out from the hardware that's available? Is it more about the building? Is it more about the programming? Is it more about the the use of resources? It's what is the focal point? Or you can have multiple focal points, but what things do we want the students to achieve? And that could be dictated by the area or the place in the curriculum where you are, or it might be slightly more open-ended, and you get a bit more freedom to let the students explore these problems in a way that they see fit. For example, if you really wanted to focus on a specific computational skill, for example, you would design the project to make sure that they have to encounter and engage with that computational construct to be able to solve the problem. So thinking about the curriculum up front, and is it achievable using the hardware and the equipment that you've got? And and also, is it actually solvable? That's one thing you should always ensure, is that once you've written the context and you've written your success criteria, is that it is actually achievable given the constraints that you're setting, as well as the hardware and equipment that they're setting. And you should absolutely do the project yourself first to make sure it's achievable, because especially when you're new to this, you can sort of come up with some wonderful ideas, and then you try to go through it and you'll trip up over several elements, or there'll be some limitation in the software or the hardware or the engineering bit of it, or resources which you hadn't thought about beforehand. So it's worth testing this on yourself, because the stuff that you trip up on, this kids would definitely trip up on. So it's worth thinking about that. And it's also like, if you're using a sort of a technology project, what are we trying to do? Are we trying to automate a process? Are we trying to gather data on a particular project? Are we trying to make a smart something? There's lots and lots of different ways to bring in wider technology aspects, like Internet of Things, machine learning and those sorts of things. So there's all sorts of different ideas and factors that we can factor into this when coming up with a project. And so whilst this helps to complicate the narrative setting and the contextualization, these are all the different elements that you can think about. So there is a multitude of different ways to create a project. So Another thing to consider is also the idea of open-ended problems. Now, it's good when you're writing success criteria for projects to start with something quite constrained, such as the device or the project needs to do X, Y, Z. But as you get towards the end of the success criteria, or even in your stretch goals, it's worth adding in some more open-ended problems. And this not only allows you to differentiate upwards, it also allows you to allow your students to flourish and be super creative in how they add in additional functionality, different features, and that's really where they can show off. And whenever I've done these projects, the more able students will go away and surprise you with what they add in. They will meet the success criteria and then go beyond it and add in other things that you hadn't even considered. And then this is the sort of thing that you can take those additional ideas that the students have come up with and add them into the next time you deliver it with your class or a different class or a different age group to enhance the difficulty or the complexity of that project. So it's worth constantly be looking at what your students are doing, because every time I've done this, for example, the micropet project, different groups of students have come up with different ideas, which I thought, that's brilliant. Why didn't I think of that? So it's a good idea to be mindful of that. But an example of how do you have open-ended problems is define what they have to do, but not necessarily have it too contrived. So make, for example, like with the micropet, make the artifact interactive. And so interaction can mean a lot of different things to different people. And then they have to develop 3 distinct interactions. So you're giving them a number of interactions, but you're not saying what those interactions are. And the interaction can be defined as almost anything. It could be something very simple, or it could be something quite complicated. So you're leaving the door open there for creativity and innovation. And I think that's really, really important with these projects, is that you don't just have a set of tracks that the students have to follow and they have to jump through hoops to finish the project. They do that to start off, so you're guiding them in the direction you want them to go, but you're allowing them to be creative and add in more complexity if they have the time, capacity and resources to do so. So it allows students to really show off. So another thing to think about before we get into the actual writing of the project is, what are the other sort of the design considerations? So I've mentioned this before about, is the context that we're going to come up with, and this is like almost a checklist about when you do come up with a context, and you may have one in the back of your mind already. You may already be thinking, I want to do a project for maths on XYZ topic, but will it motivate your learners? Is it relatable to the curriculum that you're currently covering? Are the students going to be able to understand where to get started? And it's a good sort of acid test, really, is that when you come up with this problem, and if you give it to a class, if you can just give them the success criteria and they can start on the project and know what to do, that's a good sign that it's relatable, it's well contextualized, and they understand what the context is. If they get stuck because they don't understand the context or the concept, then it needs a little bit more work and a bit more iteration. And this is why using a context which is something that they that's not new to them, that isn't new to them, is really quite useful, because it allows you to build on that prior learning. And also, don't overcook it as well. Don't overburden the learners. Even though they might be doing a project on something that they've already learned or aware of, sometimes simple is effective. And so you can use this as a tool to reinforce learning and draw together different curriculum areas or different areas of the curriculum to allow students to demonstrate their skill and knowledge of that by drawing different elements together into something slightly more complicated. So don't overburden a particular subject domain when you don't need to. And also thinking about how do you make sure that they've progressed enough? Have you given them enough time? And also, is there enough support material? And again, this is all stuff that you'll become more expert at as you develop these sorts of projects. And once you've delivered a project 3 or 4 times, you'll have it in a sort of peak condition where you know exactly what scaffolding you need to give to your learners, and you know that the context works and they can relate to it. So it's you're never going to get it perfect first time. And the projects themselves should be iterated on, just like we advocate students to do as well. So let's jump into the thick of it in terms of the examples of the projects and where we want our learners to go. So where do we start? I would advise you to think about these 4 areas. So which one of these is going to be your priority? And you could create a context from any 4 of these, and we will have examples of these 4 things as we go through the next few examples. The first one we're going to look at is a cross-curricular or a feature-focused one. So it's more of a sort of a product focus one, and it's going to be linked to a drama project, but we'll get to that in just a second. But pick one of these to get started with, and this will help sort of shape what you want the learning to be, and it allows you to sort of then come up with some ideas, come up with a context, and then gap fill the rest of the rest of the project, or the rest of the success criteria, and allows you to design something which is realistically achievable. And again, by focusing on one of these things, it allows you to then write a simple narrative explaining why you're doing what you're doing. And then once you've got that narrative, you can then come away with the success criteria. And when I'm writing these, sometimes I write the success criteria first. Sometimes I write the getting started bit, or the construct, the narrative first. It doesn't really matter which one you do first, as long as they both relate to each other and are accessible by your students. You may already have a context which your students will engage with, and you need to come up with the success criteria, but sometimes it's easy to start with the success criteria as a starting point, because then you can link that really clearly to your curriculum. And then when you have come up with these ideas, do have a go at building it yourself. I can't emphasize that enough. It's really important that you can go through this stuff, because that gives you an idea about what scaffolding the students may encounter. So that's a sort of a good place to start in terms of designing this. And when you come away from this session and want to design your own one, think about those 4 areas and which ones you want to start with. So let's jump in and have a look at the first example. So example 1. So this is going to be a drama project. So this is sort of probably one of the more difficult ones to create a project-based learning activity for, especially one that involves physical computing. And this is an example of the sort of thing you may do in your school to link together different departments and add in some digital features to their curriculum. Lots and lots of subjects now, we're seeing this globally, are starting to bring in computing and computer science as a way to enhance the learning within their subjects. Maths has been doing it for years, but areas like drama, they're taking learnings from how like theatre is using technology to make better shows, and they're building that into the curriculum. And here's an example of what might that look like. So for example, here's the context. So the school is putting on a production, and they want some light and sound to be automatically controlled by gestures. So I mean, straight away there you can see how we can use technology to do this. So a gesture is like a movement or a pattern of movements, and then that can be sensed by a device. So for example, on a microbit, it has gesture recognition on it. There are some predefined gestures on the microbit that you can use if you want to keep this simple, or you can get them to program their own gestures, which could be a series of different movements. And then we need then that to trigger something else. So we're really going to need 2 microbits for this. So you can see once we've got the context set, so we're going to be creating something that recognizes gestures, and then we need that then to trigger some sort of light or sound, or something which is going to enhance the performance. And then the last bit there, the theme of the production is left open. So the production could be whatever works in your particular local context. It may be a film, it may be a theme, it could be almost anything. I'm going to use an example of Harry Potter. So the gesture is going to be sort of flicking the wrist, like that they're holding a wand, and this allows you to then, for example, add the microbit to a wand, and then that will then help recognize the gesture, and then that can then transmit some data to another microbit, which would then trigger some sort of light or sound. And you can start simple with this. For example, the light or sound could be just on the other microbit. So let's say you get you write a program that the microbit, you flick the wrist, it recognizes that through sensing the G's or the acceleration. It then transmits something using the radio functionality on the microbit. The other microbit then picks that up, and then the lights could be just on the LEDs on the microbit, or it could play a particular sound on that microbit. Or you could, even if you wanted to go really fancy, you could use that microbit to control an actual real light and sound setup in a theatre, for example, and that's completely possible if you've got the requisite peripherals. So that's just an idea of the sort of thing that you can do with this. Now, linking the success criteria to the context obviously is an important bit of it. So the success criteria is create a device that recognizes when a gesture is performed. So they're going to have to take in some input, and then it's going to have to process what that input is. Does it meet the criteria of what the gesture that we're looking for is? And then the output would be transmitting that signal to another device. And then it says design 3 different pairs of gestures and actions. So they're going to be replicating that, but having sort of different types of outputs. And then that will allow the the learners to be creative and have fun with what gestures do they recognize, and can they do all three of them separately without sort of cross triggering the different algorithms on the microbit. So there's an element of sort of interaction and automation here that they need to consider when they're doing this, and it allows them to have a bit of play whilst they're doing it. So that's one example of this. And so the gestures could be a dance movement, it could be a flick of the wrist as we talked about, or it could be something slightly more complicated should you wish to. So there's our first example, and we're going to look at how that can be explained using an IPO table. So here's some examples here then. So the first gesture could be a shake. Another one could be sort of free fall. Now you can imagine that's part of a dance or a performance or something like that. And then gesture 3 could be 6G. So this is like recognizing really vigorous movements, which could be almost anything. It could be like a fight scene, or it could be a very vigorous dance movement. And you'd want the students to design what these gestures would be, and then test to make sure that the gesture recognition algorithm that they're writing matches that, and they can trigger it consistently. And that's the important computational bit there to get right, and that sort of speaks to the physicality of the project, because they have to be able to test this and iterate on it to make sure that they get it right. The process then is to, once this gesture has been recognized, is to transmit that data to another microbit, and then that would then trigger a light, a sound, and a set action. And what I mean by set action is something like that could be the background moving, it could be a curtain being lifted or dropped, it could be some animatronics, almost anything. It could be like a smoke machine, all sorts of different stuff that this could be, and these can all be triggered using these electronic devices. And as you can see there on the output, you could link together a light sequence using DMX, which is a sort of a theatre technology which allows you to automate and create scenes, and you can trigger those using technology such as the microbit or Arduinos or Raspberry Pis or whatever. It's incredibly sophisticated, and this is where you can lean on the expertise of colleagues. If you've got the computer science teacher bit can do the input gesture recognition, and then the output bit could be done by the drama students or drama teacher, linking together the different technologies in the different subject areas. And then the output then again could be the sound on the microbit, as we mentioned, or it could be something like an instrument or a sampler, or even something on a PC, or a prop set as well. So there's lots and lots of different things that we can use the microbits to trigger in this example. And you could see you could use these in really, really clever ways, and this really sort of sets the imagination going for the learners about how can they translate a physical movement to a like a light show or sound effects, or a combination of all three. That'd be the real sweet spot, is if they can do a particular action like a spell, for example, or something like that, and then you have all this light and sound and dramatic effects going on triggered by that movement. And so that's a really interesting thing to pursue in a way of linking together different curriculum areas. So here's some examples of some code that could be done on a microbit to demonstrate what that looks like. For example, with music here, you've got some on shake, so the microbit would recognize what shape is on there, and then it would play that sound, and it would this square wave type of sound. Any of you that are familiar with music or synthesizers will recognize that as a sort of a laser type sound. So that would play that noise, and you've got some blocks there sort of showing you how when the second microbit receives that a signal transmitted by the first microbit, then it would then play the sound. And they can design different. There is a synthesizer, or a very simple rudimentary synthesizer built into Make code, as you can see there on the right. And so the idea is that they have one microbit, it has the gesture, it's transmitted via radio to a second microbit, and then you could have like a microphone or something similar on that microbit to play that sound through the PA system or speakers in the school hall or wherever you're doing the drama lesson. So there's just an example about the sorts of things that you can do for a drama project. So let's moving swiftly on to a second example. So the second one we're going to look at is geography. So this is a school context. It's we're going to take an area of the curriculum. So if we look at the subject focused first, this is going to be using elements of data collection and sampling, which involves field work, and then there'll be some quantitative data analysis looking at percentiles specifically in this area. So let's have a look at how that relates to the context. So the head teacher is concerned about air pollution levels in the school. when there's pick up and drop off times. Obviously there's lots of traffic that come in around at schools at drop off and pick up times, and so they've asked you to create a device that monitors air quality at different times of the day. So you can see straight away that we're going to be gathering some sort of data. We're going to need to be storing that data and then analyzing it at a later time. The hardware for this, you can do this on any device really. You can connect air quality sensors to this. They're available for all of the major boards, and then they'll allow you to store or gather, store and process and transmit this data however you see fit. So how that context then relates to the success criteria, they have to build this device. It has to be able to measure the air quality. It has to be able to do it over the course of a day. So if you think about things like, power, is it plugged in? What does it do with that data? So it says the device should either store the data locally or transmit it. So you've got some options there, allow students to think carefully about how this works. You can obviously transmit the stuff over Wi-Fi, over radio, over Bluetooth, or over a wired connection as well. There's lots and lots of different ways to interpret this. What's going to work best in the context of your school, because some places you'll be able to leave this stuff in a box strapped to a post, others you might have to hold it, so there's different ways of considering this. And then lastly, you need to analyze the data and create a report. So they not just have to gather that data, they have to be able to interpret that data and do some quantitative and qualitative analysis on it, and then make some improvements or make some suggestions or recommendations about how to improve the air quality. And that might be about having people queuing in a different place, or having the number of vehicles limited to a certain number, or something like that. There's lots of different ways that could be expressed, and it's down to the students to gather that information using technology. So that's the field work, and then doing data collection and sampling to make an assessment, and then doing some quantitative and qualitative analysis on what they're doing, and then showing where the spikes are in the day, and then suggesting ways to improve it. So that's geography through and through. And you could link this as well to the sciences. I'm sure there's elements of pollution and sort of air quality in the other subjects as well. You can look at what does air quality actually mean in terms of the sort of the particulates that are in there. What does that mean from a chemical perspective? What are the biological effects of these particulate matter in the air to the human body, and all of these sorts of different things that students will be learning about, and it's just drawing them together in this project. And ultimately you'd expect students to come away from this recommending that students spend less time being exposed to this particulate matter during the peak times. So you can kind of assume that that's going to be the case, and the extent to which they can justify that using their report is the sweet spot for this project. So for an IPO table for this, they can measure lots and lots of different things. The particulate matter sensor is probably the most sophisticated way to approach this. It's also the most expensive, but they could use other things for this as well. For example, like temperature sensor, air pressure, lights. You can get various gas sensors like CO2 and the like, and oxygen sensors. You could even use an analog, for example, like a microphone that can detect when there is lots of noise, so when there's lots of traffic. So there's various different ways of modeling the inputs for this using different sensors, but a particulate matter sensor will be the best way to do this. How do they process that data? What is an ambient level of particulate matter, and when does it peak? So they need to think about how do they take those thresholds and how do they program their device to be able to measure it, and when does it alert you if it gets above a certain limit or something like that? How does it take that data and store it meaningfully programmatically? So is that going to be in a variable? Is it going to be a list? Is it going to be in a graph? There's lots and lots of ways to think about that. The processing of the graphs could be done on the board, or it could just be simply stored as a CSV and then analyzed on computers later. There's lots and lots of different ways to think about this, and the output could just be the CSV. It could also be the transmitted data over Wi-Fi, radio, or whatever, or it could be, for example, like warning lights. You could build in additional functionality which students could then come up with. So yeah, there's lots and lots of different ways to think about how this can be implemented. You can also build in some sort of Internet of Things idea into this. For example, here is an EnviroBits. This is something that you can use with a Raspberry Pi, and then there's a air quality sensor there as well that you can see plugged into a Raspberry Pi. And you can also transmit that data to cloud-based services. For example, there's one called Luftdaten, which you can see there. and it allows you to transmit this data from that sensor to the cloud, and then it does all the graphing for you. So that's like proper IoT, you know, proper networking. And so it takes away some of the analysis learning, but it does give you nice graphs showing you all of the different elements over the course of the day, and it allows you to make some more qualitative assessments based on, and because the quantitative stuff has been done for you, so it kind of lowers the learning curve a little bit, which is, I think, is really, really useful. It's an interesting element of data science to explore. So example 3, this one we're going to focus on music, and this is going to be based upon the features on the device. So we're going to be looking at the board in particular. So this is going to be using 4 version 2 microbits. So that's the starting point. And so why do we need 4? We'll see when we look at the context. So the context is we're going to be creating an autonomous digital band, and they're going to play a random tune, so there's an element of automation here, in the key of C. So you can see how this links to music. They have to understand what a key is, they have to understand what the key of C is, and they also have to understand the sort of the makeup of what a band is. So we'll have something like bass, mid, and treble to do that. That's the band essentially, and then the 4th microbit is the conductor. So the band needs to be triggered by a button press from the conductor. And the conductor also needs to be able to change the movement of the song. So it's not just pressing a button and it plays random notes in the key of C. It has to be structured, and then at the press of another button, it needs to be able to change either to another key or to a different arrangement. So that's a couple of different things they have to factor in there, and they have to be able to program the devices, or the microbits in this case, accordingly. So how does that look like in terms of success criteria? Because that sounds relatively complicated straight away, and I think it is, because not only do they have to understand the music theory, or at least the beginnings of music theory, because you'll see when you play around with make code that doing things within a particular key is automated to some degree, so it's relatively straightforward in the software. But they have to be able to think about this from a computational element, and they have to be able to get the 3 band members to play the right notes, play it in the right what's the word? Element. So there has to be bass, mid, or treble. So you get high, low, high, mid, and low notes, and they have to work together. So if they're all in the same key, it will work, but they're getting the timing right, and so that it doesn't just sound like a random mesh of notes is the important bit. And then, as it says there, playing random melodies in the key of C, and it is triggering from another one. So they have to understand how the radio frequency transmission bit works, and it has to be able to trigger all 3 of the band microbits all at once. So you can see the subject focus there is what bass, mid, and treble are, what harmony means, what a key of C is, and also how would you automate note composition, and to what extent do you automate that as well. And you might even want to link this back to the first project that we looked at, using gestures. So a conductor for an orchestra, they wave their arms around, they have a baton, and you could program this so that if it recognizes a certain gesture, it changes the arrangement of the music that's being played. So you can see this could get complicated really quickly should you wish to, but the sort of the base project is accessible, and you could simplify this, for example, just having 1 microbit being the band and 1 microbit being the conductor, and you can have it playing multiple notes. But the idea of this is that they're linking different devices together and getting them to do distinct things, and how does that change how they program these different things. And so designing this is interesting. And you could, for example, you could have each of the bands looking slightly different as well. So when they're building the artifact, it has to represent the note or the type of instrument that it's going to be playing. So there's all sorts of different things to consider when developing this project. So that's a really nice sort of cross-curricular one, thinking about what is available on the features. And this is why looking at this from the hardware perspective is important, because a microbit V2 has a microphone, it has a radio receiver or transmitter, and it has a speaker, and it has music making features within the software. So this fits all the elements for this project really, really nicely. Whilst like a Pico, it's not as easy to do that. You can add in the peripherals to do that, but it's not quite as simple or as accessible for this type of project. So this is why it's worth considering that. So let's look at the IPO table for this project. So here we go, and as you can imagine, it's relatively straightforward. You press a button or create a gesture for the input. The process is that they have to write a random music algorithm, and it could be completely random, or it could be sort of predefined arrangements, and they will need to have a separate arrangement that they can program for the other button press. They need to have some sort of radio transmission, and this is where you need to think about when you're using multiple microbits, is about you have to program the conductor and the band members to differently. So one of them has to transmit the signal, the other one has to receive it and then do something with it. So the inputs and outputs are switched. So just think about that and get students to think about how they design that, because it can get confused very, very easily. You could even play the music through speakers as well. You can attach headphones to microbits relatively easily using crocodile clips, and so you could play that through something quite louder. So this would be a nice thing again to link to the drama project around triggering sounds through gesticulation or gestures. Here is some really, really good examples, and we'll share these links in the chat. Here's some really good examples of people that have done a project very, very similar to this, where they have multiple devices which they're programmed to play noises and sounds and effectively be one big band using all the technology available on the devices. So do have a look at those after this project. Bear in mind that it's music constantly throughout, so yeah, save clicking the links until after the session. But there's some really, really creative examples here of the sorts of things that you can do with music with these devices, particularly microbits, but you can do it with any of the other boards as well. It's really clever, creative stuff. And if you have music colleagues or you're a musician teacher yourself, then yeah, please do check these out, because it's a really good confluence of music and technology. Okay, fourth project, and this is the last one we'll look at in today's session, and we're going to look at this from the point of view of the curriculum, and this is a physics problem. Now this is a classic physics practical type of activity, and this is where we want them to, or want students to be able to measure acceleration and be able to control independent and dependent variables, and also be able to factor in human error and scale. So and then whilst doing that, also be able to identify anomalous and average data. So this is the sort of thing that you would typically do in a physics lesson. You'd have a ramp, you would have a trolley, and you would change the variables like the steepness of the ramp or the surface of the ramp or the types of wheels, and then all of these things you can change, and you would measure how quickly it went down the ramp or how quickly it accelerated using a stopwatch. And so there's an awful lot of room for error there, and this is why these experiments are useful, because controlling the variables is difficult. And what we can do in this is seek to automate and get some really accurate data using technology, but you still have some of the same problems around when do you trigger the release of the cart, and when does it stop measuring, and all these sorts of things. So there's a lot of different things that the students need to think about when they're doing it, but if they can get those physical elements right, it allows them to have incredibly accurate measurements of acceleration, and even be able to measure the acceleration in real time going down the ramp and play that to a screen or transmit that data to another device, or they can measure the acceleration in a CSV, which they can then look at on a computer. So there's an awful lot of different stuff that they can do here. So the context is quite simple. The physics teachers asked them to create this device to accurately measure the acceleration of a trolley down a ramp. So they're basic. The success criteria is where the detail comes in, though, because they have to create this device to be able to accurately and consistently measure it. And they must be able to control the independent and dependent variables to mitigate human error, and that needs a little bit of unpacking. So ideally, before this lesson, they will have talked about or learned about what dependent and independent variables are, what sort of human error might creep in, and how can you control for that when developing this project. So it might be worth even doing the classic way of it, or delivering this lesson in the classic way, using ramps and trolleys and stuff, using a stopwatch first, and then talk about what the weaknesses of that approach are and how inaccuracies can creep into the data, and then doing it digitally using devices such as this, and then analyzing the data and comparing the two, which gives you better results. Did the additional complexity help with the analysis, and all that sort of stuff. So this is a good example to bring in your physics colleagues to develop these projects for them. And you can see it's equally valuable to both departments, which is I think that's a really important thing to get right, is that every different subject matter that comes into this, you can apply technology to it to improve it, and in this case through accuracy of measurement. So the IPO for this, this is a very sort of a basic implementation, but you might start it with a button press, and that might be like the cart rolling over the button, for example, or it might be the button being pressed as it takes off, or it might be the button releasing, for example, as it goes down, so that you can consistently release the button, and having another button at the bottom to measure the stop time or something like that. And this is all stuff that the students need to think about when they're designing this, is that how do you make sure that each release of the trolley is the same? What sensors do they need to log that data, and how often do they need to, what's the sampling rate of that, and what do they do with that as well? Do they transmit it, do they store it, do they graph it on the LEDs? There's a multitude of different ways that they can interrogate this data. So hopefully that's got your creative juices flowing in terms of the sorts of things that you can do with these projects. And so just to sort of draw it back to technology, all the things we looked at sort of involve electronic devices, but you can also use the idea of the Internet of Things, or IoT, as a context in and of itself. Everything can have a device or a sensor or something put in it, and it can be programmed to transmit data to the cloud via the internet, over Wi-Fi, over 5G or whatever, and then it can be analyzed in the cloud using various different networks. So that allows you to do the sort of the physical IT data capture. It allows you to do the computer science bits of programming the devices. You've got the physical element, the engineering concepts of how they put all this stuff together, and then you've got the data science and with the maths and physics analysis that they can do on the data, depending on which context you've used to gather the data. And you can apply almost any subject area to the application of IoT. You can use it for almost anything. And also related to that is the idea of data science. This is an emergent subject, and you can use data science for to enhance any area of the curriculum. Where should it sit? It obviously involves maths and statistics, especially around the machine learning element of it. It also involves computer science and IT, because you have the hardware elements and you have the programming bit of it, but you can apply it to any subject domain. Taking accurate measurements, just like in the last example that we looked at, and then using digital devices to get more accurate measurements, and then it gives you lots and lots of digital data to interrogate. It opens the doors for creativity in terms of how you can apply this to almost any subject. You can imagine, for example, like in sports, you could have a device which measures you could attach it to like a cricket bat, let's say, and then so you can measure the telemetry of a cricket bat, and you can have one at either end of it, so you can get a really good idea about exactly how the bat moves and when the ball hits it, and these sorts of things. And you could see and you can log when a run is scored, and you could even have trackers in the ball as it flies through the air, and you can see which player is performing the best, what strokes, what acceleration, what angle is the best ones, and so you can use that to help train and improve the performance of your players. So it's just an example of the sorts of things you can do for this. You can apply it to any subject at all. So let's briefly recap on what other devices there are available, as we've looked at the microbit version 2 as examples throughout all of these projects, but there are other boards available too. For example, there's the Raspberry Pi 4, you can see there on the top left, which is a fully competent board. It's very powerful, got a very powerful chip on it, lots and lots of RAM, lots of ins and outs via the USB and Ethernet ports and HDMI, so an awful lot you can do with that board. It's got a full operating system on it running Linux, so it's very capable. And there are other boards such as the Pico as well from Raspberry Pi, which is a much more simpler affair. It's got the microcontroller on there as well as USB and a button, but little else. So you have to add in additional peripherals to make that do what you want it to do. And this is a factor to consider when choosing a board. What language do you want to program in? Because some boards can only handle some languages, and also what built-in functions do you want, or features do you want on the boards? Some of the Arduino boards come with some peripherals built in, some don't. Same with the Raspberry Pis, and same with the microbit as well, which comes with a lot of ins and outs as we've discussed so far. But some of the boards don't have any at all other than an LED and a button. So it's worth considering these as a factor when designing your projects. So that's the session really. Those are all the different things you need to think about when designing and developing a project-based learning experience. And now it's over to you. The call to action now is to, using the templates that we've shown earlier, is to come up with your own project-based learning project. Come up with your own contexts, and then once you've written the context and the success criteria, and you have a lesson around that, try them with a class. Just give it a go over a lesson, and then once you've finished that class, reflect on that, iterate on that project to improve the delivery of it. there's always going to be ways to improve the delivery of it, the speed of it, the pace of it, and just bear in mind as well that you do have to work quite quickly, or the students have to learn quite quickly when they're doing this, and so it's worth geeing them up to go faster as they go through it. And that's something that when I've seen this delivered is people tend to go too slow at first, so just bear that in mind. Pace is key here. And then once you do have your project and you're confident that the project works well, write more. And when you do write more, share them with colleagues, share them with peers online, share with your colleagues how to write project-based learning activities. You can apply this to, as I say, any subject. And then when you do have something that works really, really well, share them with the ARM School program. Share them via social media, share them with your communities of practice and with your peers and with your colleagues. Because these, when they work, are really, really, really powerful teaching and learning tools, and it's really, really useful to be able to share this expertise that you've developed and these resources that you've developed with your colleagues to help everybody use project-based learning and physical computing effectively. So hopefully today you have you've seen all the different elements that make up what physical computing projects are, what a context is, why contexts are important, and all the things you need to think about when creating a project-based learning activity. And again, don't forget the ARM School program schema. That's really important to help frame how you write these projects, and please do use that as much as possible. So if that was interesting and you want to learn more about project-based learning and physical computing, then please do check out our courses on edX. These are called Search for Project-Based Learning, and there are 4 courses on there, of which we've taken elements of this course from the practical application in the classroom, so course 2, and we'll be looking at other areas over the coming months from the other courses. So do check these out. They're all freely accessible on edX.com. There is a cost for the certification, but the access to the courses is free of charge. And I hope you've enjoyed today's session, and if you've got any questions, please do put them in the chat. Thank you very much.
Well, before we move on to Q&A, I think we'll just pause to discuss feedback, which we'd like you to provide on the session. Surya, if I could hand over to my colleague Surya, she's just got a couple of things to mention on this before we move on.
Thank you, Nick. Hi, everyone. I have shared the feedback link in the chat box. So I request all the participants to share their feedback in the link.
Excellent. Okay, yeah. So we'd love to hear your thoughts on the session and to gather your feedback. So do please click on that link and complete the questionnaire as soon as you can. Okay, let's move on to questions. Rob, a question really about going back towards the beginning of the training on planning time. What is there additional planning time? Because it looks like I think from the structure involved in developing PBL projects, there's a lot of work that you need to do before the lesson and before you can get started. Can you give a sense of how much additional work is required compared to perhaps a more traditional lesson?
Yeah, I think it will always, at first, when you first start using project-based learning and planning lessons using these principles, it will take longer at first to plan a lesson than what you typically would. But as you become more experienced, you'll speed up. It's as I went through in this presentation, there are lots and lots of different elements you need to consider. And once you've been through it once and you've seen the sorts of things that learners will trip up on and how you can structure these activities to best suit your learners, you'll get quicker and quicker at doing it. But there's no avoiding it does take longer to plan these lessons out first, but mainly because of your unfamiliarity with that process. But essentially, you can write these lessons relatively quickly if you've got a context which you know will work with your learners, and you have an understanding about the subject area that you want to apply it to, and the hardware that you're going to use, and then you've written that success criteria. That is often enough for learners. And when I've delivered this with older learners, sort of like 14 to 18, then that's all you need. You just need the context and the success criteria, and that is all. And that can be written quite quickly if you are familiar with how these things kind of interoperate and how they're structured. With younger learners, obviously, you need to scaffold it slightly more, so you need to have more support material and think about the pace of it a little bit more. And there's also the when you're delivering this, as well as the speed you go through it with your learners, because as they become more familiar with this pedagogical approach, they will get through it quicker. So you will need to adapt how you run the lessons given the experience of your learners. So there are quite a few different moving parts here that you need to think about. But yes, it does take longer initially to plan these, just because of the unfamiliarity of it. But as I say, you will speed these up. And I say I've been writing these for years now, and I can, if I've got an interesting context that I want to explore, I can write them in sort of 10-15 minutes. And then the longest bit really is running through the project yourself. Because it's a really good idea to test that, as I said in the presentation, just to make sure that you can do it, and you can obviously do it a lot quicker than your learners will. But it's worth doing that just to be sure. So yes, that's it. It does take a bit longer. There's no avoiding that, but you will get faster.
Excellent. Another question on context. So to what extent can learners decide their own contexts for a project? Can you simply give that as a task for them, and for them to develop what it is they want to do within a project as on an individual basis, and let them get on with it?
Yes, absolutely, you can do that, but I wouldn't start there. And the reason for that is that because of all of the different complexities that I've described in this session, is that there's a lot to think about, and students aren't going to be aware of all of those, and it takes a bit of practice to do that. So you can give them an open book and say, right, choose a global goal and solve a problem in one of those global goals. But I'd maybe do that after about a year of doing these PBL projects in a typical classroom, because there's a lot that can go wrong with that. And maybe if you did want to give them a completely blank canvas, get them to just design what a project would be without actually physically programming it or developing it. So you could just do a sort of shorter session where they fill in one of those design templates. But I wouldn't start there. I would, because you can't then control what subject elements that they explore, what the context is and how it relates to your normal curriculum. So that's very kind of open-ended learning, which can have its place. But if you want to keep them aligned to the curriculum, I would structure it more formally yourself through giving them a context and a success criteria, just to keep them on track.
Okay. So I've got a question in about coding. So what about, would you have on hand a sort of solution for the programming element of the project that you could use as a reference point for yourself as a teacher, but also hand it out to students when they needed it?
Yes, and it's a good idea to develop one of these anyway. For example, when you first design your project-based learning project, you should go through it yourself. And as you're doing that, you will be creating a solution. So it's worth saving that and having that to hand as a reference to yourself in case students get stuck. I wouldn't give the solution to the students, obviously, because then that just kind of takes away the sort of programming learning from it. But it's you can use that as your scaffolding. So for example, if you've got learners that need some additional scaffolding, you could give them prompts based upon that solution, or give them snippets of that code to help them along, but use it sparingly. You want the students to come up with this stuff themselves, so don't just give them a solution, because that's not really helpful to their progress, unless you're really pressed for time. But again, it depends on where you want to focus the learning. If you want them to really eke out the engineering elements of it, or that, you might want to just give them the code. But that's a real missed opportunity for them to flex their computing muscles, and it's what makes it truly cross-curricular.
Yeah, and I think it's worth also just reiterating that you can see more examples of projects that are structured in this way if you go to school.arm.com, where our courses also include guidance for teachers. So there is additional support there if you need it. I think on a related point, actually, to the last one about the extent of the information that you provide to learners. What about learners that need more support? Would you ever give them step-by-step instructions to build a basic solution, just so they can get it, have something to show?
There is a place for that, certainly. I mean, in the OmSchool program resources, there are books which sort of handhold through the entire solution to the project, and that can be a valuable tool. But that also does add in some additional learning curve, because it has to be they have to read through it or follow a video or something like that. So this additional resources need to be created, which adds in additional time. And it's the whole point of sort of project-based learning is that they discover the learning, but within a structure or within the confines of what you're trying to teach them. So you can give them sort of, well, you don't really want to give them a 10-page document with every step label that they need to do, because the nature of the success criteria, if they're written well, it has an open-ended element of which you can't possibly capture all of the different permutations of that and write solutions for them. So following a sort of a step-by-step sort of didactic approach can be useful, but it kind of detracts from what project-based learning is all about. But if you're trying to introduce learners initially to physical computing and they're learning about boards from the very beginning and they've never used them before, that can be quite useful. But I would stick to the core principles of project-based learning rather than just treating this as a different type of didactic exercise.
Yeah, that's a really good point. And I think just on a couple of questions that I can see here about the practical demonstrations of the projects. So I would encourage you, if you haven't gone through the previous 2 sessions, you will find discussions about some of the projects within those that we offer within the school program. So oil spill cleaner upper, micropet. And also, if you go to the resources themselves on school.arm.com, you can often see pictures that will indicate the sort of build that you're looking at. So, for example, a template for a micropet and that sort of thing. So, yeah, we would encourage you to explore the previous sessions and also the resources that we present online, which give more context, more visuals around the sort of projects that we've been discussing today. So that answers the question also about attending previous sessions later. They're available. They're available online through the registration link. Okay, I think we have one final question, which is so sort of in 2 parts really. With a more traditional approach to teaching and learning, I can see individual learners' progress. So things like by the questions they've answered, the topics they've covered. How do you keep track of learner progress in PBL on an individual level when you have teamwork, etc., going on within the classroom and different people progressing and doing different things in terms of the complexity of their builds?
I mean, that is a classic problem with group work generally, and that applies equally to project-based learning. You don't necessarily have to do project-based learning in groups. So if you need to assess the individual's progress on a particular topic, you may want to give them a project which they do individually. But that obviously increases the overhead in terms of the technology and the resources that you need, because rather than having them in groups of 4, every student needs one. If you do so, project-based learning is a great way to engage your learners, to get them to work collaboratively on a project. It's not a fantastic tool for assessment, although especially formal assessment. And this is why you wouldn't use a PBL project for an exam, for example. So whilst you can assess elements of it, and you can do that through observation, and you can get them to conduct formal assessments such as like MCQs, like multiple choice questions and things after the fact, sort of assessing their knowledge of what they've done so far, and you get them to do that individually. So you can apply assessment techniques to project-based learning, but it's not really designed to be used as an assessment tool. Not to say that you can't assess the learning that's gone within it. You just have to think about it in a slightly different way. So yes, I wouldn't treat this as sort of exam prep. It's a different methodology. It's a way of sort of solidifying and making concrete learning. But the method of doing that learning isn't directly accessible unless you've got lots of people there observing and writing things down, which is obviously impractical in a classroom setting.
Excellent. Okay, I think that's the end of the session in terms of the Q&A. So thank you very much for the questions that have come in. Thanks, Rob, for the main session and helping out there with the Q&A as well. So I think it really just remains for us to thank everyone for coming. Very much appreciate you spending the time at the end of your day with us. We would very much encourage you to go to the previous sessions and explore those too if you haven't already. And of course, if there are topics within this within those sessions that you would like to explore further, do visit edX.org and search for Teaching with Physical Computing. You can enroll for free and explore these ideas and this way of teaching in your own time. I'd like to also thank once again CBSE, Dr. Saha and Mr. RP Singh for their support of this webinar series. Our next one is in January. So January 18th, another Wednesday, and that is From Play to Projects. Rob, would you like to say a couple of lines on the next session?
Yes, so this next session is looking at the approach of sort of play-based learning, which is almost like a precursor to project-based learning, and how this sort of the activity of engaging with these projects can be simplified for younger learners, but how you can still structure it in using sort of PBL practices and pedagogy so that you can get learning out of them. And this, it's taking it from just a random assortment of playing tasks which students might be given into something which is useful to alignment to the curriculum, and you can ensure that they are learning something along the way. And so it's a way to sort of introduce learners to project-based learning and sort of gear up younger learners to prepare to learn in this way.
Excellent, great. So we hope to see you then in January.